All right, welcome back. And today we're going to still continue our discussion. Well, we're going to finish that today, actually, about the comparison of two populations. Okay. So far, what we did was we discussed how do we test hypotheses and construct a confidence interval about two samples of interval or continuous data, right? So we assumed that all of our measurements were numerical. We dealt with independent samples or matched pairs. Well, sometimes you're dealing with data that is not numerical in nature, but it's categorical. And remember, we discussed what can you do with categorical data. Not a lot, right? So, first of all, you cannot compute the mean. Whether it's ordinal or nominal, there is no mean. Median applies only to ordinal data. Mode is, we cannot test the mode, really. Okay, there is no standard deviation for the categorical data. So the only thing that we can actually test for categorical data are proportions, right? All right, and so if data are nominal or ordinal, that's what we're going to do. Just like for the continuous numerical data, we're not going to test proportion in the population 1 versus proportion in the population 2 separately. We're going to test difference between pi 1 minus pi 2, where pi, we discussed that, right? Greek letters are used in statistics to denote the population, right? Mu is population mean, pi is population proportion, okay? So if your data are categorical, nominal, or ordinal, your entire population has the true proportion of certain category, certain response, pi, okay? And 1 refers to the sample number 1, 2 refers to the sample number 2. So the idea basically is that just as before, we have two of these, right? The difference. All right. The idea is just like before. As much as we like to know the actual population proportion, unfortunately, it requires access to the full population data, which oftentimes we cannot get. So therefore, we're going to base our judgment on samples. So from population 1, we get sample. From population 2, we get sample. They don't have to be same size, can be different. In fact, in the example that we're about to take a look at, that's precisely what happens, different sample sizes, okay? And from that, we compute the sample proportion, p hat. It's different from pi, just to illustrate that what you compute from the sample is not exactly the same as what you get from the population. And after that, we basically formulate hypotheses in terms of pi 1 minus pi 2. So we're not testing separately pi 1 and pi 2, we're testing the differences. Same idea as we had for the continuous data, okay? There are a lot of applications actually, and one of the problems that I assigned today for the homework deals with exactly this type of scenario. You have, so for the homework, I'm going to assign the problem when the operations manager wants to buy a new machine, for example, to manufacture details or parts, okay? Some parts are defective, some parts are good. And the machine, obviously, you want the good machine that makes low percentage defectives, right? So if you have to make a choice between machine 1 and machine 2, you want to take a look at what percentage defective parts both of them are making and pick the one with the lowest, right? So therefore, you run, trial production on first machine, on the second machine, and see how many parts you have defective, find the percentage in both samples, and then compare, right? That's one example. Another example is marketing effectiveness, and that's actually what we're going to take a look at in just one sec. Market shares of the product before we run the advertising campaign and after, okay? So, for example, let's say before we controlled 15% of the market, then we ran advertising or changed the product somehow, made it better, customers like it, and now our market share went up, okay? Political pollsters also use this type of approach. Comparison of the approval rating before and after. Every week now, the approval ratings are being published by the Gallup, what's it called? Gallup organization, right? Polling organization. And they say that the approval rating hits historical low, right? So from the previous week, approval ratings were 42%, now they're 39%. That is based on a sample, right? So on the face value of it, it looks like approval rating went down. Well, if you run the test, it may not necessarily be true, right? If you compare proportion 1 minus proportion 2 against 0, you may find that this actually, like 2% down based on the sample, doesn't really mean that they're down. It could be just a sampling, random sampling effect, right? Pharmaceutical companies use that a lot. See, pharmaceutical companies, when they, like, let's say, for example, aspirin, painkiller, right? So if you have a headache or backache or something, right, you take aspirin or Advil or another painkiller and it works, right? How do we measure if it works? Well, there is no painometer, right, that you can hook up to the human being and it says, yep, your pain level is 74.5. That doesn't work that way. It's based on the subjective feelings, right? So therefore, you have to give a drug to a person or group of people and ask them, what do you feel on the scale from 1 to 5, right? And they subjectively will tell you. And then after that, you can run the analysis. But again, you're testing really percentage of people who are in the severe pain versus percentage of people who are in the severe pain after they took the drug, right? And now you're comparing them. And to see if the drug works at all, you can compare that against no effect, which supposedly is placebo. You heard placebo, right? The term. Placebo means what? Sugar pill, exactly, right? It's like piece of calcium, right? It has no active chemical ingredients, but the idea basically how pharmaceutical companies, for example, let's say they develop a new painkiller and they want to see if it has any effect at all compared to sugar pill, right? So they take the group of people and they give them similar looking pills, right? One group takes the actual drug, another group takes the placebo, but this group doesn't know that this is placebo. They're told that this is a drug. And then tell us what you feel, right? There is a such thing as placebo effect, right? It's a psychological thing, right? So even if I take the sugar pill, but I'm told, yeah, this is a really effective drug. So now I expect to feel less pain, and I'm like, yeah, I think it's working, but it's not chemical, obviously, right? It's not the chemical component. It's a mind trick, really, right? So probably part of the reason why people feel pain is, their brain tend to over-amplify what's going on, right? So if they're told that, yeah, that's going to help, and I feel less pain, but it's not chemistry that's working, really, right? It's not the pill. Okay, anyhow, let's take a look at this problem. Product enhancement. Close to marketing, actually, right? Consumer packaged goods company is test marketing 2 new versions of soap. So soap is exactly the same. They didn't change the product itself, but they developed 2 versions, 2 packaging for the same soap. Okay, one is brightly colored. These are the best pictures that I could find several years ago online. So take it with a grain of salt. So one of them is really cool looking soap, brightly colored, plastic wrap with big letters, very attractive soap, right? Another is just gray box dull soap. So they want to see if one soap will do better than another. And if you would choose, which one do you think has a better chance to sell? Brightly colored or the dull? Brightly colored, probably, right? Because humans tend to, well, not all the time, but we tend to shop based on what we see, right? We see a cool looking product, we got to have that. So here's what they do, okay? They pick up 2 supermarkets as a test market. Supermarket number 1 sells brightly colored soap. Supermarket number 2, we ship to them old version, which is dull, gray looking, very boring kind of soap. If there is such thing as fun soap and boring soap, right? So brightly colored is fun. Okay, but we're not the only people, not the only company who sells soap through the supermarkets. There are 4 other companies, A, B, C, D, or 1, 2, 3, 4. So competitors, right? And here's what we ask both supermarkets to do. Can you please track every time when you sell a bar? Obviously, they're recording which soap was that. Was it ours? Was it competitor A, B, C, or D? And then we tell them, can you give us at the end of the week summary of all your sales? So like every sale is recorded, Every single bar that you sold is recorded. And it's also recorded what company, what brand did you sell. Okay? All right, so all this information, all this data are recorded to the file. And we expect the brightly colored soap to outsell the dull colored soap, right? More specifically, not just in numbers. Like we sell more bars in supermarket number 1. It could be that supermarket number 1 is bigger in general, right? It's located in more densely populated area, it has more customers, etc. Right? So we're not just looking at numbers sold because other companies can also sell more bars. We're looking at the higher proportion, right? That our soap in total sales represented higher percentage. That means that we grab higher market share. Okay? So let's take a look at the data. Let's go back to Scholar and jump data sets right there. Yesterday I posted the file called soap sales. So go ahead and open up the file in jump. There it is. So if you scroll all the way down, you will see, well, first of all, actually, 2 columns of data, right? Brightly colored soap and the dull version. All right. What type of data do I have here? Well, let's take a look at what the data are. So this one, for example, says that competitor C was sold. So that means that the first record of soap sales in the week for this supermarket number 1 was competitor C soap was sold. And then C sold 2 more, then A, and then B, and then there was our soap that was sold. And then we have D, our soap. So every data point really is not a number, right? What type of data is that? Obviously categorical, but what type? Is it ordered or not? Company A is better than company B. Nothing quite like that, right? Just 5 competitors on the market. So therefore, we're dealing with nominal data. Okay? And if you scroll all the way down, let's try that actually. If you scroll all the way down, you can see that sales are not the same, right? So supermarket number 1, where we placed our brightly colored version, sold total of 904 bars, right, during this week. Supermarket number 2, where we placed our dull version, randomly sold more, 1,038 bars, okay? So let's take a look at percentages, at proportions, okay? So let's go to the distribution. And I'm going to highlight both of these columns and look at the distribution of both variables. All right, so here is the bar chart. It's not a histogram, right, because there is no ordering of columns, right? It's pretty much in the alphabetical, well, is it? In the, no, probably it's not in the alphabetical order. Our soap, A, B, C, D, competitors, right? So, bright version, our new, advanced, cool packaged product, right? We're looking at the sales of 180 bars, right? Out of total 904 bars that they've sold. So therefore, our sales are responsible for 19.912, almost 20%, right? Of all sales of the soap in supermarket number 1 was our soap. That's the bright version, okay? Now let's take a look at another supermarket where we sold the dull version of our soap, okay? So we sold 155 bars out of total sales 1,038 bars, right? So that's responsible for 14.933, so close to 15%. So judging by these numbers, and these are only samples, right? So that we're clear, it's not everything, is just 2 samples, two stores in 1 week, what they can sell. Judging by these 2 samples, does it look like our bright version grabs additional market share compared to the dull version of the soap? Yeah, it does, right? It went from almost 15% to almost, right there, 20%. So it looks like if you package things differently, people will come by it, right? So we're going to grab a bigger market share without changing much of the product characteristics, but just the way it's presented, right? It's all in the presentation. So there might be some truth to the statement that if you package, if you use a more attractive package, that will generate more sales, more market for you. Okay. Now, of course, we need to test this thing, right? Because it's all based on samples, and therefore we don't know if it's a random fluke, if this 5% difference between the market shares really a statistically significant difference, right? It can be just random fluctuation. But before we do that, let's actually use our flowchart. Let me go ahead and open the flowchart. Yeah, right there. So again, what I want us to do is be able to look at any problem, any statistical problem, and follow this decision tree flowchart to find out which test do we need to use. Okay, so obviously we're comparing two populations, right? Sales of brightly colored soap and sales of the dull colored soap. Data type is nominal, right? Data type is nominal. And number of categories, well, technically it's 3 or more, right? Because what we have is our soap, competitors A, B, C, or D. But do we really care about all the other sales individually? Like how competitor A is doing, how competitor B is doing? We don't, right? So we can think of that as every bar of soap that sells, it's either ours or it's not, right? And it doesn't matter what's the company that produced the other bar, right? It can be competitor A, B, C, or D. It's a competitor, okay? So every sale that's made in the supermarket, we view as, is it ours or is it somebody else's, right? And we care about only our percentage, right? So even though technically we have 5 different categories, but you can combine all the competitors into one category and say, well, that's what we're interested in, to see what percentage of our sales and what percentage of sales that does not belong to us, okay? So we're kind of creating 2 categories only out of 5, right? So we're really looking at 2 categories. And there you go, it's a z-test for the difference of proportions, P1 minus P2 in the entire population. Okay, so now let's go back to our slides and let's actually discuss what exactly are we trying to test. All right, so my alternative hypothesis, I'm going to write it out first in plain English, okay? I'm going to pick, for some reason, hold on, we're experiencing technical difficulties. Let me go ahead and reopen it. Imagine that. All right, so what I'm trying to see is if my brightly colored soap will outsell in terms of the market share, not just in terms of pure numbers, right? But in terms of the market share, it will outsell the dull version. So that becomes my alternative hypothesis, right? And I'm running low on the batteries, so therefore I'm going to switch just to the slides, okay? All right, so I'm trying to see if the proportion of sales for our soap bright version is going to be higher than proportion of sales of our soap dull version. That means that the market share for the brightly colored soap is going to be higher than the market share for the dull colored soap. So I'm going to improve my market share by just changing the way the product looks, right? So since we discussed everything that we do has to be formulated in terms of difference, pi 1 minus pi 2, I have to modify this thing. Very simple, right? By subtracting, for example, dull version, proportion of the dull soap sales from both sides, and therefore on the left side I'm going to have difference between the bright and the dull, and that's supposed to be greater than 0, right? That would mean that my bright colored soap grabbed higher market share, okay? And therefore, if I reverse that statement, that's going to become my null hypothesis, that difference between sales is not greater than 0. It's the same or less than. All right, now the next slide, I was kind of going to modify that, but didn't have time yesterday. So let's go straight into the testing of the hypothesis, right? So I am going to switch back to jump. And let's remember these numbers, because that's pretty much how the test will work. Basically, we need to supply the test with only 4 numbers. Sample size number 1, that would be 904. I'm going to write that down. 904 is sample size for the brightly colored version, right? And out of these 904, 180 were our sales. So bright sales, 180 out of 904. My sample number 2, size was, that's a dull soap, right? 1038 for the dull soap. And our sales were 155 bars out of these 1038. But these are the only 2 pieces of information really that the test requires. Okay? And how do we find the test? Actually, it's not one of the regular menus. That's a little weird, but it's hidden in the help menu. So I'm going to close that one because I don't need that essentially anymore. So if you go to the help menu and go to the sample data, then right here under the teaching scripts, which we used before, right, for distribution calculator, there is a group that's called calculators. And if you expand that group, you will see different links. The last link says hypothesis test for 2 proportions. That's precisely what we're doing, right? We're testing P1 minus P2 for the categorical data. So I'm going to click on that link. And first thing it says is, they want to feed the calculator the raw data that you have in the jump file or the summary statistics. Well, we already have summary statistics, right? Brightly colored soap sold 180 bars out of 904, and dull colored soap different numbers. So I'm going to pick summary statistics. You can pick either one of them actually, okay? So if you feed the raw data into the calculator, it will do all calculations for you. But let's see how it works with summary statistics. So I'm going to say OK. And first of all, it says, well, you're going to test P2 minus P1. So now let's go ahead and enter our hypothesized difference, right? So going back to the slides, what are our null and alternative? We're comparing difference between proportions with 0, right? So our hypothesized difference, according to the null hypothesis, is 0. So I'm going to go back to the calculator and say hypothesized difference is 0. Okay, good. Now, it says you're going to test the difference, P2 minus P1. So according to my records, this is my P2, right? What comes first, so that I'm consistent with what jump is saying. And that's my P1. Okay, so P2 is sales of the brightly colored soap. And P1, to be consistent with jump, is sales of the dull colored soap. So I have to enter bright colored soap as P2, right? So I'm going to go back. So here is my P2. That should be numbers referring to the brightly colored soap. So what are they? It says, what's the count? How many bars you've sold of the brightly colored soap? 180, right? I recorded that before. I remember that from those times. 180 bars out of total sample size for the brightly colored soap was 904 bars they sold, okay? Altogether, including ours, competitors A, B, C, and D, everything. Now sample 1, that would be dull colored soap. Dull colored soap we sold 155 bars out of total sales in this supermarket was 1,038 bars. Okay? And significance level is 0.05. So I have my numbers, summary statistics already set up and entered. Make sense? Now the only thing remaining is I need to pick which one of these options do I want, right? It says select your alternative hypothesis. Is it P2 minus P1 not equal to whatever you hypothesized, greater than or less than? Well, let's go back and see. So we're testing bright minus the dull market share is greater than 0, right? So going back to jump, That's my 0. That's what I hypothesized difference must be. And alternative is greater than the hypothesized difference, right? And that should be it. Let's see. Let's see what I'm getting. Here I have sample 1 proportion. These numbers actually we knew already, right? We looked at the summary distribution of both samples, of both columns, variables. And we know already that proportion number 1, that would be dull soap, is close to 15%, and proportion 2, that would be brightly colored product, that's close to 20%. So these numbers we knew. Then it says, here's the difference between these two. Okay, so it looks like the brightly colored version grabs additionally close to 5% market share, 0.0498. And then a couple of miscellaneous calculations, z-score, etc. And then at the very bottom, here is my p-value for the test that I'm conducting, right? So the p-value is 0.0019. It's less than 1%, right? So what do I do with less than 1% p-value? Do I keep the null or do I reject the null? The p-value for the test is right there in front of me, 0.0019. I reject the null, right? It's a small p-value. It's less than smallest alpha that I can use, 1%. So between the null and the alternative, if the p-value is small, I reject the null, and my alternative states that, yes, indeed, this difference between percentages between the market shares is statistically significant, right? So the brightly colored soap does in fact grab higher market share than the dull colored soap. Make sense? So the answer to the original question, will the company perform better in terms of the market share if they just change the packaging? The answer is yes. They will perform better statistically, and the test proves it, right? Now let's actually talk about the extension of this problem. So these slides, they basically repeat what we just did, okay? But here's the extension. Extension of the problem is like that. So now that we have established that brightly colored soap grabs additional market share, and now it sells the dull version of the product, my operations manager comes to me and says, hey, look, I understand that you guys want to switch to the brightly colored version, right? But the reality is the dull packaging was cheaper, okay? And bright packaging is more expensive, so therefore it's not just enough to say that, yeah, we will gain additional market share, whatever that might be, but we need to make sure that the additional market share that you grab, guys, is at least 3%. Not just at least over 3%. Okay? Only then our increased costs of production and packaging will be offset by additional sales. If it's 3% or less, then probably we shouldn't do it, because we will start losing money. New product is more expensive. So it's not just bigger market share, but we need over 3% higher market share. Okay? And then, since I didn't take the BUSN 31 class, I'm not familiar with statistics, what do I tell him? I tell him, look, man, of course it's more than 3%, right? Not only it's more than 3%, it's nearly 5% actually, right? Because according to my sample proportion 2 minus sample proportion 1, the difference is 4.98%, almost 5%. So, yeah, rest assured, we're in the good shape. We did grab more than 3% market share, but my operations manager, he's smart, he says, well, don't you know these are point estimates? Appearances might be deceiving, so you have to test the hypothesis, my friend, right? And what hypothesis do I test now? Well, let's go back to the slides, right? The hypothesis that I test now is that the difference between the market shares of the bright soap minus the dull soap is gain that I created, additional market share, right? It is more than 3%. If that's the case, then yeah, we should do it, because even though it's more expensive, it's worth it, right? We will be able to cover our costs easy, right? Otherwise, if it's 3% or less, then probably the answer is no, even though it's higher market share, but it's not big enough of the gain. to cover the extra manufacturing costs, unfortunately, right? So the only thing that I have to change in terms of what I test is the hypothesized difference, right? That's it. Because I'm still testing proportion of the bright minus proportion of the dull, but now I'm comparing it not against 0, but against 3%. And how do I say 3% in terms of proportions? 0.03, right? That's my hypothesized difference now. Okay, so I'm trying to see if the bright colored version minus the dull colored version market share exceeds 3% of the market, 0.03. Okay, and now when I hit enter, it recalculates the p-value for me. Of course, none of these things change, right? Sample 1 proportion is still for almost 15, sample 2 is still almost 20, so no differences there, okay? But now my p-value changed because I'm comparing that against a different value, p1 minus p2, right? It's not 0 anymore, it's 3%. So now my p-value is 0.1248. So what conclusion do I make from this? P-value is relatively high, actually, right? It's higher than 10%, my p-value. And alpha equals to 10%, significance of 10%, is the highest one that probably I'm ever going to use. So therefore, my p-value is high compared to alpha, and I keep the null hypothesis. I fail to reject that in favor of alternative. And what was my null hypothesis? My null hypothesis states that difference between market shares, in other words, additional market share gained by the brightly colored soap, is not greater than 3%, unfortunately. Statistically, I do not have a proof. Okay, so what I see the difference in my samples, what looks like 5%, in actuality it could be a random fluctuation. Okay, the difference is not that very different from 3%. So what looks like 5% and what can be 3%, they're not statistically different from each other. So therefore, unfortunately, as much as I want to introduce new product, I cannot, based on these two samples, I cannot state that my additional market share exceeds 3% and the switch over to the new product will be worth it and cover the extra manufacturing costs. Okay, so when my operations manager told me that, hey, we need to test hypothesis, he was actually right, that it might not be necessarily that, clean-cut case, right? What looks like 5% on the point estimate level doesn't look like that actually when you test the hypothesis. Okay? Make sense? Will you be able to do something like that on the exam or the homework? Test proportion differences and compare that not necessarily to the 0, but to maybe something else. Because homework probably asks you to do exactly that, I believe. Okay? All right, so any questions about testing two populations proportions? All right, so let's take a 10-minute break. All right, and after that we're going to start discussing comparing more than two populations. Okay, now we're going to switch gears a little bit and keep exploring our course structure. So we're going to learn some new tests today in the rest of this lecture. Just as a reminder, kind of a review, what we did so far in this class is using our flow chart, right, of the class. We learned about describing a population. We said that data can be interval, nominal, and ordinal. And for interval data, you do the t-test. For nominal and ordinal data, you do the z-test for the proportion. Or in case if you have more than one proportion, chi-square, goodness of fit, right? Okay, so we're pretty much done with this part some time ago. We just finished half of this tree, all right? And that tree would be comparing two populations or more. So let's review what we can do. When we have two samples coming from two different populations, data can be interval, and we're always interested in central location, right? So samples can be independently collected or matched pairs. In case distributions are normal of samples or there are sample differences, we're using the t-test. Well, we never actually asked ourselves, what if they're not normally distributed, right? What if differences are non-normal, or one of the samples, maybe both of them, are non-normal? Then what? And we can't use t-test, and we have to use something that's called non-parametric techniques. That part we're not going to cover until probably a week from today. So that's going to be the last part of our course. What if the normality assumption is violated? And we can't use t-test, and we have to use something else. Also, we discussed that if your data are nominal and number of categories is equal to 2, then we're using z-test for proportions. We just looked at the problem, right? About this brightly colored soap and the dull colored soap. Were you interested in sales of your soap or your competitors? That part we didn't discuss yet, and that part we didn't discuss yet. What if your data are ordinal? Then what can you do? So all these tests are non-parametric tests. We're going to look at them at the end of this class. So far, we're going to be, for now, I mean, we're going to be pretty much done with comparing two populations, and we'll come back to that at the end of the semester just to see what happens if you're dealing with ordinal data or your normality assumptions are violated. So let's move to the next decision tree right here. Okay, next decision tree, I'm going to zoom it in, just like that. What does it say? Comparing 3 or more populations, right? And again, we're going to study, first we're going to start with interval data. 3 or more populations means that you're dealing with multiple samples, right? Not just 2 samples, as we did so far. You can have 3 samples, 4 samples, 5 samples, and they're being compared in one shot, okay? So that type of analysis is called ANOVA, analysis of variances. And let me go ahead and bring the slides up. Okay, ANOVA is applied when you're using, when you're dealing with comparison of 3 or more different populations. So let's kind of discuss what ANOVA is, and then we'll do a couple of problems, fairly simple problems. Well, first of all, ANOVA stands for analysis of variances. And that is the test, like I said, that's used to compare together in one test 3 populations, 4, 5, 6, there is no limit. It can be as many as you want populations compared. The test was developed about 100 years ago, okay, and one of the first applications actually was in agriculture, but we'll discuss that in just a couple of minutes. It's fairly powerful and widely used test. Now, the test is a little weird, quite honestly, because when you read analysis of variances, variance has something to do with inconsistency in the sample. We discussed that, right? Every time when you have a distribution, you have an average, or mean, or the mode, or median. That basically is a characteristic of the center of your distribution. Another way to characterize the same distribution is kind of reverse side of the other side of the medal, right? Variability. How inconsistent your data points are around the mean. They can be fairly close together or they can be far away, and that basically, the variance speaks to the inconsistency, okay? This is a weird test, I got to tell you, because it uses variation to compare the means. It's kind of a blend of two things, right? Mean and the variability. So far we were thinking about mean, the center, and the variability as 2 completely separate characteristics of the same data set, right? 2 populations can have the same mean, but very different in terms of variability. So these 2 kind of are not related, right, to each other. Well, this test actually kind of blends the difference, right? So it starts to erase the difference between the idea of the center of the distribution and the idea of the variability. We're actually using variability to compare the means. That is weird. All right, so ANOVA, in one test, like I said before, can compare multiple populations together. Okay, so you have k samples. K can be any number, k columns of data, numerical data, and the test is extremely easy to formulate. It's very simple. Okay, our null test is our null hypothesis is going to be that all samples, all populations have the same exact mean. They're not different from each other. And our alternative is going to be the opposite of that statement, right? If the null says that all the means are the same, alternative says not all the means are the same. Simple as that. So it's very easy to formulate. It's very straightforward. Okay. The ANOVA is actually very similar to the chi-square distribution. In what way? Remember when we used chi-square distribution, goodness of fit? It was Pearson's chi-square goodness of fit test, right? What did I tell you about the chi-square goodness of fit test? That this is like a smoke detector in the house, right? If there is a smoke detector going off, does it tell you where the fire is? No, it doesn't, right? Maybe there is no fire, but it still goes off, right? So the fire can be in the kitchen, in the bathroom, anywhere, right? In the garage. The smoke detector doesn't really tell you that, okay? That was chi-square distribution, chi-square goodness of fit test. ANOVA is kind of like that. It's a smoke detector. It can either tell you that the means are the same, or it can tell you, no, they're not the same. But if they're not the same, it's not going to point out to exactly what happens, okay? Exactly which means are not the same. So the test is powerful, but it has its own drawbacks. All right, so here is the idea. Let me kind of briefly illustrate the reasoning and logic behind ANOVA. I have k populations, as many as I want. It can be 3, 4, 5, 50, doesn't really matter. And I want to compare the means, mu1, mu2, mu_k. Now, we discussed that many times, right? The only way how I can know mu1, mu2, mu_k is when I have access to the entire population data, which is not happening likely, right? So therefore, I have to rely on samples. So I take sample 1 from population 1, I take sample 2, sample k. They don't have to be the same size, can be different. And what I compute from each sample is sample averages, x1 bar, x2 bar, xk bar. Now I need to use my samples to judge how close populations or how far apart are they, right? In terms of their central locations, in terms of their averages. That's what ANOVA does. Well, let's keep that one. I want to illustrate. I'll come back to this slide. So here is how the test is being performed, ladies and gentlemen. Let's say that my null is true. And now in the ANOVA, do I have it somewhere? Hold on. I just want to give you a preview. Thought I have it somewhere here in my slides. What? Yeah, then no, that's not it. Null and alternative. Oh God, where is it? Yeah, that's the one. So here is how the test is being formulated and performed. My null is always going to be like that, right? I have k populations. Null hypothesis will always state that all k populations have equal means. They are not different from each other. Always, okay? So it's a very straightforward test in terms of how it's formulated. And my alternative actually, it's kind of a little bit funky. My alternative should say not all the populations have the same average, right? They're not equal to each other in terms of their averages. But there are many different ways how that can be the case. For example, let's say that my mu1 and mu2 are the same, and the rest are different from them. That's one way. Or maybe all of my means except for one are equal, and one is very different from the rest of them, right? Or half of them can be equal and half something else, right? Or all of them can be different. So there are many different ways how not all the means are the same. So therefore, statisticians write the alternative in this way. Okay? That pretty much covers all the possible cases, where it says at least two populations have different means. They all may have different means, but at least two are different. That violates the null, which says that they're all the same, right? So this is how the test is being performed. And again, when we start hypothesis testing, always, what do we assume? We assume that the null is true, right? It starts with the assumption that the null is true. Same thing happens with ANOVA. So let's go back several slides, and let's take a look at this one. So if all the means are the same, null is true, right? And the null says that means are the same. What will it tell you? The average of my sample 1, shall I have, no, that's the slide. Yeah, the average of my sample 1, I'm going to call it x1 bar, is close to the average of sample 2, x2 bar, right? If null is true. I can expect all of my sample averages to be close together. So they're all close together, and if I combine all samples in one big super sample and compute the sample average for that super sample, I'm going to call it x bar bar, grand mean, so to speak, right? So if all of my samples or all of my populations are very close together, they have very similar, very closely located means, then x1 bar, x2 bar, xk bar, and also x bar bar will be close together, right? They'll all be grouped in the same location, approximately. So here is the weird part, okay, about the ANOVA test. When ANOVA test is performed, really what we are computing, let me see if I can go back and find that. What we're really computing is, yeah, it's not here. How far is my x1 bar from x bar bar? Well, I can find the difference, right? Distance. x1 bar minus x bar bar. And then I square it, because distance can be positive or negative, right? How far away my x2 bar, sample 2 average, from the grand mean? Same thing. I'm going to take the difference, x bar 2 minus x bar bar, and square the distance, right? And I do the same thing for every single sample that I have. So essentially I'm combining the expression that looks a lot like variance, what we did for the sample. Remember the formula for the variance? You have to find the mean, and then distance to the mean for each observation, square the distances, add them together, and divide by n. That's your variance, right? So we're using very similar expression in the ANOVA test. I'm creating the variance, but the variance is based on how far my sample averages are away from the grand mean for all samples. So it is a weird thing, right? I'm creating a variance expression from sample averages, and then after that I have to judge. If that variance is large, that means that some of my samples are far away from the grand mean, which means that probably not all means are the same, and I find in favor of alternative hypothesis. Okay? If, on the other hand, the sum of squared distances is small, that means that all the sample averages are close to the grand mean, and probably null is true. So that's the intuition behind the ANOVA. Okay? It's using the variance-like expression to test the sample means. That's the weird piece, okay, about ANOVA. Now, let's discuss new terminology, new definition, okay? A factor of study. We actually did that already when we talked about two populations. Remember when we compared two populations, what was the example that we used in class for independent samples, for example? Do you remember what we used in class? Oh my God. Goggles. Yeah, exactly. Goggles. Right. There was a problem about the U.S. Olympic Committee, right? And they had two suppliers of goggles, and we wanted to see if one supplier is better. We used actually analysis tool in JUMP that forced us to create a stacked column, right? Remember that? We stacked two columns, and that created a third column where it said which sample that observation is coming from. And when we ran the analysis, it said, what is your measurement? That would be depth, how deep under the water goggles start leaking, right? And what is your factor of study? And factor of study was company or supplier, or manufacturer, right? We're trying to see if the choice of the manufacturer affects the quality of goggles, right? So essentially, that was kind of a first time when we saw the idea of the study factor. So therefore, it's not exactly new for us, but let's review that. What's a study factor? Study factor is common classification among your samples, among your population. Okay? So in my goggles problem, it was a company. Sample 1 comes from the company Thorndike, sample 2 comes from the company OptiView. So I'm studying if the supplier selection has any effect on the quality of my goggles, right? So something that unites or is common among your populations or columns, that is called a factor of study. So they're common classification criterion, whatever it is we're trying to run, right? K samples will represent actually K levels of this factor, okay? So when we compared one company to another company, we had only 2 levels, right? Supplier 1 and supplier 2, that's it. If you have more than 2, then you have multi-level factor. Sometimes factors are also called treatments. The history behind that term actually comes from 1920s. One of the first applications of ANOVA analysis was in agriculture. Okay, in agriculture, you know that people are using fertilizers, right? In order, why do people use fertilizers? What's the big idea?
Increase the yield.
Increase the yield, exactly right. You provide more nutrients to the crops, and therefore they, gain weight quicker, so increase the yield. In 1920s, when the world was mostly agricultural, like U.S. economy, for example, the U.S. economy was primarily, growing food, agricultural based. People were trying to find out if some fertilizers, some nutrients are better than others. And there are a lot of different ways how you can provide nutrition to the plants, right? You can fertilize with phosphates, you can fertilize with nitrates, so there are a lot of different possibilities, okay? So here's what statisticians did back then in the 1920s. They said, let's take several fields, same crop, for example, corn, okay? And let's treat field number 1 with phosphate. Let's treat field number 2 with nitrate. Let's treat field number 3 with whatever else is out there, ammonia or something like that, okay? So let's pick, let's say 10, 15, 20 fields, right? And just apply different fertilizer to each field. And then when the crops show up, we just measure on the per square foot basis, or 10 square feet area or whatever it is, right? What was the average yield of the crops given that we treated that specific field with that specific fertilizer? So therefore, if you consider 20 different fertilizers, you get 20 different fields and 20 different yields, right? From 20 different fields. And because they treated the field with a fertilizer, essentially it's like a column, it's a variable, right? In your data set. A sample, okay? After that, every sample that you're getting in the ANOVA analysis, not just called factor level, but sometimes called treatment, remembering those times when we used ANOVA to see if there is a difference between different fertilizers. You treat the field with a fertilizer, so therefore you collect a sample, and the sample is referred to as treatment. So factor levels are oftentimes called treatment, okay? All right. One-way ANOVA. That's the first model that we're going to study. What's a one-way ANOVA? One-way ANOVA is when you have only one factor. Okay? One factor of study. That happens when you collect samples independently from each other. So what we did before, when we said, well, if you compare 2 populations, you can have independent samples or matched pairs, right? So one-way ANOVA is a 2-population analog, or rather multi-population analog to independent samples. Samples are collected independently from each other. They are not linked, they are not related anyhow. Okay? We collect sample 1 randomly, sample 2 randomly, sample 3 randomly. There is nothing that links them among themselves. All right. Now, let's look at the specific problem. Okay, marketing strategy. A lot of our examples come from marketing area, right? Which marketing strategy is better? So suppose there is a juice company that makes apple juice and sells that through the retailers. Okay, apple juice company would like to introduce new product to grab new market, and that would be apple juice concentrate. So basically, it's a can with this, sugary apple tasting content inside, very concentrated. And the idea basically is you buy it from the store, you bring it home, you get big, jug of water, right? You put the content inside, you stir it, dilute it with water, and you get yourself homemade juice, but produced out of concentrate, right? So a company would like to start offering that product to the customers, but they're not sure how to advertise, how to market that. So here are three ideas. One way how you can create a commercial is to say, well, that product is convenient because, it's small, it does not require refrigeration, it does not take space in your fridge, because when you open apple juice, probably you want to refrigerate it, right? Otherwise, it will go bad. So therefore, it's more convenient, buy it. Another one is quality. Okay, some people are concerned that quality may deteriorate if you're using concentrate, right, instead of the organic thing. So quality is same as regular juice, or maybe even better. So quality doesn't suffer. That's another way to advertise. And a third way to advertise is it costs less. Okay, why? Because, well, we're skipping a couple of steps in the manufacturing process, right? We don't bottle the product, so there is no adding water, stirring, and bottling part. Okay, when it comes to the distribution and logistics, we can distribute more concentrate because it occupies less space, right? So overall production costs and logistics costs are lower, and that translates into lower prices to consumers. So these are three ideas that they kind of kick around. They don't know which one to go with, so they decide, how about this? We're going to take 3 cities, and every city is going to be our test market. So in city number 1, we're going to advertise based on the convenience. In city number 2, we're going to run different commercial that pushes the quality. In city number 3, we're going to promote price. It's lower price, so therefore people go buy it and save some money, right? All right, so after that, the company places the product into 3 different cities, runs the commercial, and they're waiting for the results, right? And what are the results? Sales. How many cans are being sold of this concentrate are being sold in the local stores? Not all of them, but just a sample of stores, right? So let's take a look at our sample. Let's go back to Scholar and jump datasets. There is a file called advertising.jump. So let's open it up. Advertising.jump is right here. Okay, so I have 3 different columns that represent 3 different advertising strategies, right? So in each column I have 20 stores, right? Let's say, for example, I'm tracking sales during a week period of time, 1 week. So in city number 1, I advertised based on the convenience. So I said, well, 20 stores, 20 weekly sales. In store number 1, I sold 529 cans. In store number 2, 650, and so on, right? City number 2, I ran the quality advertising. Quality is not better or worse, it's pretty much the same. And these are the numbers, right? And in city number 3, my advertising revolved around the price. So now I want to compare these 3 columns and see if any advertising approach gives me better or worse results, okay? So, first of all, true or false, these samples are independently collected from each other. More specifically, if I look at line number 1, there is nothing that links this number 529 and that number 804 and that number 672. These are 3 different cities, completely randomly picked, right? So there is nothing that links these 3 cities. So all of my samples are independently collected, right? Let's actually go back to flowchart. right? I want to get into the spirit of Christmas, so to speak. Okay? So statistics is a decision tree. That's it. Depending on which problem you're dealing with, is it one population, two, three, or is it a relationship, you have to pick a certain starting point, and then after that answer a series of questions. What data you're dealing with, what design did you use, is it normal or not, if that applies at all, and then it arrives to the test. Okay? So, based on what we've seen in our file, where do I start? Let me zoom out. Do I start with looking at one population, looking at two populations, three or more, or is that a relationship problem? What do you think? Based on what I see in the file. Three or more, right? I have three populations compared against each other. So I'm going to zoom in. No, not quite like that. Hi. Right here. Three or more populations. Next question is, what data are you dealing with, my friend? Is it interval, ordinal, or nominal? The answer is interval, right? These are all numbers. We're dealing with continuous, numerical, interval, however you want to call it, data. Next one says, experimental design. What do we have? Independent samples or something else? We just discussed that we are dealing with independently collected samples, right? CT1, bunch of stores. CT2, a different bunch of stores. There is nothing that links these columns. Okay, and the next question says, well, the required condition, of course, right? Every test in statistics comes with a required condition, pretty much. If populations are normally distributed, then you have to use one-way ANOVA. If they're not, then this is a non-parametric test. So, let's test normality, okay? So, before we proceed, let's test normality. I'm going to go back to the data, and remember how we did that, right? How we tested normality. We want to look at the distribution of our samples. That's number one. So, I'm going to pick all of them, so that I see them all in one window. What do you think, you guys? Does it look? Let's make it stacked. Okay. This one, does it look normal to you, or is it a little weird? Kind of weird, right? This one is better, right? The second one is better. That one is even weirder, right? It looks bimodal. Oh God. Maybe I'm not that lucky this time, right? Well, let's see. Let's look at the normal quantile plot. There it is. Is it well-behaved normal quantile plot or not so much? Looks pretty good, right? How about the second city, where I advertise based on quality? Yep, this is it. What do you think? Is it a well-behaved plot? Yeah, looks decent. And last one for the price, normal plot. Also not too bad, right? Okay. I could also fit, of course, the let's fit the continuous curve into the weirdest. That would be the number 3, right? That's the weirdest. Well, let's see if the weirdest one is actually more or less normal. So I do the continuous fit, normal, fitted normal distribution, goodness of fit test, and I'm looking for high p-value, right? Only then data are normally distributed. Here's my Shapiro-Wilk test, which says 0.6. That's big, right? So data are normal. And if I do the same thing for the rest of the samples, I'll find same result. So in spite of the fact that they were looking weird on the histogram, they're actually not that far away from being normal. Okay, so coming back to my flow chart. Independent samples, populations, each one of them normally distributed, so I have to use a one-way ANOVA. Now, why is it called one-way ANOVA? Well, let me tell you. One-way ANOVA is because there is only one factor of study. Okay? Remember, factor of study is something that goes on in my columns, right? Columns represent different levels of something. So, when I advertise on convenience, or on the quality, or on the price, these are 3 different ways to advertise, or advertising strategies, right? So really what I'm studying in this problem is, does the advertising strategy affect the sales? So my factor of study is advertising strategy. And my response that I'm measuring, the numerical response, is number of cans that were sold. So numbers represent continuous variable, which is a response variable, my measurement. Okay? depends probably on the, it may depend on the selected advertising strategy. So the factor of study is categorical variable advertising strategy. The response variable, which depends on the selected strategy, is the sales. Okay? Now remember what we did for the analysis of the two population independent samples. We stacked them, right? JUMP requires that you stack your variables when you're dealing with independent samples. That was true for two populations. That is still true for ANOVA. So therefore, let's stack them. Okay? We tested normality. That was kind of job number one, right? Just to see if we can do the ANOVA. Turns out that we can because all of them are normal. So now we have to stack the columns. So I go to the tables menu, pick the option stack, and now I need to tell JUMP which columns I'm stacking. All three columns, right? Stack them. And then it says, well, I'm going to create two out of them, right? One will contain all the measurements, numbers. Another will contain your factor, convenience, quality, and price, right? So how do you want to call them? Well, let's call them sales. That would be data. And the label that tells me which sample it comes from, I'm going to call advertising strategy. How about that? Advertising strategy. All right. Because that's what my factor of study is, right? I'm looking if sales depend and they vary based on the choice of the advertising strategy. Now I click OK, and here is my stack data. So these are all the measurements, my dependent variable, right? It depends on the strategy, sales. Sales depend on strategies. That's my assumption that I'm trying to figure out. Do the sales depend on the strategy, or do they stay flat regardless of what strategy I pick, right? All right, and that is my advertising strategy factor. It's factor of study, independent variable. Well, and let's also review really quickly, what exactly am I testing? Remember how we record null and alternative hypothesis for ANOVA? What's my null? No, not greater than 0. In ANOVA, the null is always looking like what? All samples, or all populations have the same average, right? Let me find it. Yeah, right here. Okay, this is what I'm testing, always. My null always looks like that. All the averages are the same, are equal to each other. By the way, if this is true, if there are no differences, what does that tell me about the sales? Do they depend on the selected strategy, or do they not depend on the selected strategy to advertise? If sales are the same regardless of what I pick. No dependency, right? If sales for the price advertising, for the quality advertising, for the convenience advertising are the same, that means that no matter what I pick, it's going to give me the same result. So therefore, sales do not really depend on the selection of advertising strategy. And my alternative is like this. Oopsie. My alternative, where did it go? Right, like this. Oh my God, it's all over the place. All right, here's my alternative. At least two different populations have means that are not the same, not equal to each other. If I find in favor of alternative, that will tell me that yes, sales do depend on the advertising strategy. You pick a different strategy, you get different sales. What it doesn't tell me is which one is better and which one is worse, right? Remember what I told you about the smoke detector? That's your smoke detector. It says, somewhere there is a fire. There is a better strategy among the three that you've selected. Which one? I don't know. I am ANOVA. It's not my job, okay? I'm not going to tell you which is better, which is worse. That's not what I'm doing. I'm telling you, are they the same and there is no difference, or are they not the same? That's where it ends with ANOVA. Okay, and that's basically how we write it out, okay? Specific to this problem. Average sales that you achieve when you advertise using convenience, same as quality and the same as price. There is no difference, therefore, which strategy you pick doesn't really matter. They're all the same, there is no dependency. And the alternative says that at least two strategies, they do affect sales. They do result in statistically different answers. Okay? Well, that's the form of null and alternative that we write down every time. So from that standpoint, ANOVA is actually a very simple test. How to write out the null and alternative is very straightforward. All the same, or no, they're not. That's it. Note that we're not testing right tail or left tail or anything quite like that, right? So there is no comparison with a number. Okay. So now let's go through the actual mechanics. So I put it in the slides, but let's go to the software and repeat the same steps. Okay? All right. So every time when I run the hypothesis testing, I write out hypothesis, and next step is to get p-value, right? That's how you do the testing. P-value, compare it against alpha, and then what happens, happens. Is it more than alpha? Is it less than alpha? Keep the null or reject the null. So let's go to Analyze menu, and you have to use fit y by x, or you can just do it from the main window. There is a shortcut, fit y by x. We used that option already for two hypotheses. Oh, for two population hypotheses. Remember when we had independent samples, right? So JUMP actually is using the same tool inside the software for testing independent samples. No matter is it two populations or is it three or more populations, you go to the same place. Fit y by x. Okay. So response variable y is what? What's my response? Sales, right? How sales respond to the advertising strategy. That's my dependent variable right there. And the factor that I'm studying is choice of strategy, right? Can be quality, convenience, or price right there. Very good. So now I click OK. And first thing that it shows me is scatter plot, dot plot, right? So essentially every sample that I have, 20 observations in each sample, is right there in front of you, okay? So not a whole lot I can tell you, right? By looking at these dots. By the way, what this horizontal line represents, can you guess? It's the grand mean if you consider all three samples as big one, right? So among all these three samples, if you combine all sales together in one big super sample, that's your average right there, okay? And let's call up the statistics summary. Okay, means and standard deviations. So from the red triangle menu, we're asking for summaries. And again, we're not going to tell the whole lot from this. Kind of informally, we can judge if sales are same or not the same. But to see that statistically, we have to actually run the test. So convenience, the first column right there, right? When I advertised based on the convenience, my average sales per store during a week were 577 cans of orange juice concentrate, apple juice concentrate. Okay, if I advertised based on the price, it was 608.6, and if I advertised based on the quality, it was 653. So I'd say that between the two extremes, right, the convenience and the quality, there was a 80 item gain, right? On average, I gained 80 cans extra, but is that a big enough difference for us to claim that yes, it is big, and it is significantly different? I don't know. So let's run the actual test. Christian.
Can you answer that basically just by looking at the standard deviation and knowing that none of them are less than 8?
Yeah, I guess you can. Yeah, that's one way to look at that. But you will see in just 1 second what we're going to do. Well, not we, JUMP. What JUMP is going to do is it will show us a 95% confidence interval. And kind of informal way how you can tell that, hey, these things are the same or not the same. If confidence intervals do not overlap, that means that probably these means are very far apart, right? But if they do overlap, there is a significant portion that overlaps, then you can probably say, well, since there is a significant overlap, probably it's not statistically different thing, right? And that's pretty much like from this analysis that you see right now in front of you, we cannot say the whole lot. So we need to actually run the test, and from the test we'll see if we can gain more insight graphically. So here's what I'm going to do. Of course I have to go to the red triangle menu, right? Everything that you ever wanted to do in JUMP is in the red triangle menu. So red triangle, do you see the word ANOVA? Yep, it's right there. ANOVA, click, and look what happened. First things first, right? Let's take a look at these green weird diamonds, right? What these green weird diamonds represent is the middle line is the average for that sample, okay? The endpoints, the vertices, are the 95% confidence interval, okay? And also, I learned just yesterday, how wide is a diamond is actually, it also has a meaning. It depends on the sample size. Small sample sizes, short diamonds. Large sample sizes, large diamonds. Well, in my case, they're all the same because all samples contain, 20 observations, right? So diamonds are equally wide. Now, let's kind of informally judge what's going on, right? Before we proceed. If you compare convenience and the price, this is my 95% confidence interval, and this is my 95% confidence interval. Do they overlap a lot? Half of them actually overlaps, right? So this is the common area, right? So they do overlap quite a bit. Therefore, probably, if I'm comparing just these two, convenience advertising and price-based advertising, probably they're not significantly different, right? Now let's take a look at this pair. Price and quality. Is there a lot of overlap? Yes, there is, right? This portion is common for both of them, right? So therefore, again, if I compare them pairwise, as if convenience doesn't exist, and these are the only things, price and quality, then probably my t-test will not find a difference, right? Now let's compare convenience and quality. Do they overlap a lot? Nope. If there is an overlap, it's very teeny tiny, right? So if there is a difference, probably it exists between my convenience advertising strategy and the quality advertising strategy, right? So kind of informally, by looking at this picture, I would say, if I would have to pick which advertising gives me highest sales, I'd say quality, right? And definitely not convenience, because this is probably where the difference is going to come in, right? So what do I expect from my ANOVA test? That all the means are the same, or are they not? Probably not, right? But let's see. Analysis of variances. Do you see that part of the output? That's the one that we have to use. And here is my p-value. That's the most important number out of the entire analysis. Everything else is mechanical piece. It computes the sum of squared errors inside the treatment, between the treatment, factors in degrees of freedom, takes the ratio is distributed according to the F distribution. All these details I'm skipping because they're not interesting, they're purely mechanical, there is nothing educational about that, okay? The most important output is right here, p-value, okay? It's in the right tail of the F distribution, 0.0468. So I'm going back to my hypothesis that I was testing, and here they are. My null says that they are the same, my alternative says no, they're not. At least two are different. My p-value that we just saw was 0.0486 or 68. My short-term memory sucks. 0.0468. Okay. So what do I do with this p-value? Compare it against alpha. What alpha do I pick? In the absence of any indications, right? Which 5%. So here is my hypothesis that I'm testing. 0.0468 is my p-value, less than alpha. What do I do? Reject the null. And the null says that it doesn't really matter which advertising strategy you're picking. Well, I find differently, right? My test says that it does matter. At least two populations, they differ in terms of their means, right? But that's where ANOVA stops, right? ANOVA says, at least two are different. Which ones? I don't know. Well, after that, you can run something else, right? After that, you can run pairwise comparisons, or you can run something that's called turkey test, right? We're not going to cover them, but you probably, if I'm a manager trying to make this decision, the alternative says it does matter how you advertise. Well, great. So which one is the best, right? Which one do I pick? ANOVA doesn't tell you. This is where ANOVA stops. And you can informally judge that by looking at this, of course, right? At these diamonds. And you're saying this diamond is the highest, and it has very little overlap with convenience. So these probably two are significantly different. Not much difference between these two, and not much difference between these two, but if you consider these two, then yes. Okay? But that's informal judgment, based on what you see in the picture, right? ANOVA says, yes, they are different, so therefore your sales, they do depend on selected advertising strategy, okay? And that's one way ANOVA, ladies and gentlemen. Any questions? Concerns, complaints, sarcastic comments? Is it a weird test or is it more or less comprehensible? It's all right? Okay. One of the homework problems that I'm going to assign today is on ANOVA. So let's see if you can practice a little bit formulating the null and alternative, finding the p-values, taking the data, of course, checking for normality, right? And then running the analysis, finding the p-value, and concluding. So it shouldn't be very complicated. The test itself actually is fairly involved. If you look at the mechanics behind the scenes, the formulas, what goes into the computations, that's a lot. Okay? And I did this mistake once, a long time ago. I decided to show students how the test actually is done. We used probably this example as far as I remember. Oh my God, it took me a week to go through this thing. So that was the first time and the last time I did that. I said after that, nope, there is no point to explain the mechanical part, you know, how everything is computed and where the F distribution p-value comes from. So this is the extent how far we will go. So I know this way is a weird test. It's very easy to formulate. It's very easy to perform. But technically, it's fairly complicated. Behind the scenes, nuts and bolts of the test, they're very complicated. Okay? So this is a one-way ANOVA because we had independent samples. There was nothing that linked observations on the same line. Okay? And samples were collected randomly. One sample doesn't really care about how the other looks like. So let's take a 10-minute break, and after that we're going to take a look at the ANOVA analog of matched pairs. All right. In the previous example, when we looked at advertising based on quality, convenience, price, we discussed that all these samples come from 3 different disconnected set of stores, right? So therefore, samples are independently collected. There is nothing that links individual stores to each other. Well, this is not always the case. Remember when we discussed 2 populations, specifically interval data, like for example goggles, right? Goggles were collected independently, but in another example when we talked about starting salaries of MBAs, right? Starting salaries can depend on the GPA. Higher GPA, higher salary. So therefore, we collected data in a special way. What did we do? We said, well, let's collect finance MBA group randomly, and let's now handpick and match MBAs from marketing by the GPA. So we take one person from the finance sample, GPA 3.9. Good. Now we need to find a marketing student with GPA 3.9 and record their salary. So they were matched, right? Something like that is also possible with ANOVA. Okay? Our samples do not have to be all independent from each other. Instead of that, we can make all observations number 1 across the samples to have something in common to match. All observations number 2 to have something in common to match, right? If we do that, then we're kind of dealing with matched pairs, pretty close analog to what we had before, with only 2 samples. Only now they're not pairs, right? There is more than 2. So therefore now we're going to call them blocks. And data obtained in this way we're going to call a blocked design. Okay? Blocked design. So my next slide actually explains that, I believe, fairly nicely. So the idea is if I have independent samples, then all of these things from sample 1, x1, 1, x1, 2, etc. It's just random numbers. All things, numbers from the sample 2, same thing, right? Completely randomly collected without ever looking at sample 1. But if I take sample 1, observation 1, sample 2, observation 1, sample 3, observation 1, and make them match using again some criterion, and I don't know what is that, okay? Can be anything really. Then I'm dealing with blocks of data, right? And blocks, they can play actually a second factor that I'm considering, right? So my samples, they represent data collected about certain, certain subject, right? Certain one subject. And then if I go horizontally in a row, I can think of every block represents a certain level of yet another variable, right? So essentially, when I'm dealing with blocks, it's like as if I'm introducing second factor of study, right? First factor of study was whatever happens in the samples. In my previous example, it was marketing strategy, right? It can be convenience, quality, and price. Different ways to advertise, okay? If I match observations and put them in blocks, horizontally, in a row, that's as if one block is one level of a certain second factor, right? And different blocks, they're just different levels. So I have two factors. One that kind of goes on in my columns, and another that represents my entries, my rows, records, okay? So this way, if I have a blocked design, blocked observations, this analysis is called two-way ANOVA. Two-way because there are two factors of study. One that goes in columns, another that goes in the rows. Make sense? All right. Well, let's take a look at, first of all, what kind of hypothesis do we formulate? It's actually very simple, again, just like for one-way ANOVA. In one-way ANOVA, our hypothesis is very simple, right? Null and alternative. Null means are always the same, all of them, right? And the alternative would be, no, they're not, at least two are different. Well, now I have two factors, right? One of them corresponding to columns, another corresponding to the records, rows. So for each factor of study, A and B, I can formulate same set of hypotheses, right? Means of the factor A are the same, or means of factor B are the same, versus alternative, no, at least two are different, okay? So instead of one ANOVA test, I have actually two ANOVA tests going on. That's pretty much all the difference in terms of testing, in terms of mechanical piece, okay? So let's take a look at this problem. Pharmaceuticals example. I told you that pharmaceutical companies are among the biggest users of statistics, right? Because everything that they do, they do a lot of medical and chemical research, that's given, right? But at the end of the day, when they have to run the drugs by the FDA, Federal, what's it called, Drug and...
Administration.
Yeah, Federal Drug and Food Administration, right? Food and Drug Administration, something like that. They have to approve, and for that, they have to provide them, the FDA, the statistical evidence that they performed, clinical trials, and in clinical trials, however we measure symptoms were improved, and people started to feel better, etc., right? All of that is statistical research, really. So here is the problem. Many Americans suffer from high levels of cholesterol, which can result in bad things like heart attacks and such, right? So if level of cholesterol is very high, over 280, whatever the units are, okay, doctors prescribe drugs to reduce that. So doctors, again, don't treat you, right? They patch things up, okay? And make things to look better than they really are. They don't treat underlying health conditions, but instead they provide you a Band-Aid. Anyhow, so you take a drug, cholesterol level goes down, so the plaque doesn't form in your arteries, and therefore there's less of a chance of the heart attack. That's good. So drug company recently developed 4 different drugs for cholesterol reduction, but they're not sure if these drugs are the same or some are more effective than others. Who knows, right? So here's what they did. They selected 25 groups of 4 people. Okay? In each group, person number 1 took drug number 1. Person number 2, drug number 2, 3, drug number 3, and 4, drug number 4. Okay? But it could be that the effectiveness of the drug, in other words, how good is that with reducing the cholesterol level, it depends on how much you weigh and how old are you, right? Maybe, for example, on young people, drugs work better than on older people, and maybe if you're skinny, the drug works better. If you're, overweight, drug works worse. Who knows, right? But there can be a dependency. So the way how the groups were set up is inside every group of 4 men who were taking 2 different drugs, right? 4 different drugs. People were matched by their age and weight. All right, so let's take a look. These questions we need to address, right? Let's take a look at the data and say how many factors are there and what are their levels of the factors. of study, and then answer these two questions. Is there a difference between the 4 drugs in terms of the cholesterol reduction? And also, do age and weight affect how effective is the drug in terms of reducing cholesterol level? So it should be in the file cholesterol drugs, which is out there. That's the file that I posted yesterday. So let's download that. Okay. Let's open it up. I'm going to close things that I don't need really. Yeah. Okay, so here is my file with cholesterol drugs. So you can see that here is my drug number 1, 25 people taking it, right? Drug number 2, 25 different people taking it, right? Okay, that's all good and dandy. Do I have samples collected independently, or are they matched? Or blocked in this case? They're blocked, right? So, in other words, this number 6.6, this number 12.6, 2.7, and 8.7, they have something in common. Even though these correspond to different drugs, what was in common between them? They were taken by people who have, well, that's given, that's for all of them, right? They all have high cholesterol. But what's so special about these 4 gentlemen in the line number 1? They weight the same and they have the same age, right? They have matching age and weight, okay? So this way, remember our discussion when we talked about 2 populations. We said, why block design or matched pairs is better than independent samples. When you're dealing with independent samples, you have less control, right? For example, marketing, right? I do the marketing, I expect the sales to go up. So I take a bunch of sales before marketing and after the advertising campaign, and I report them. If I don't control my groups, my sample 1 is random, my sample 2 is random, what can happen is, in the sample I can accidentally get bigger stores or smaller stores, right? Stores which are located in more densely populated area or less densely populated area. Average income of the people living in the neighborhood are different. All of these will affect the sales, right? So therefore my marketing effect will be kind of smooshed a little bit, right? It will be more obscured by other things that contribute to my study. But if I'm doing the matched pairs, or blocks in this case, I can eliminate these factors, right? So in this case, what did I do? I said age and weight can contribute to the effectiveness of the drug, right? So if my samples are completely random, what does that mean? Well, that means that in sample number 1, for example, I get slightly older group of people, okay? And drug doesn't work that well on them. It would appear that, drug number 1 is less effective, while in actuality it could be the age factor kicking in, right? Or weight, same thing, right? Group number 3 has less average weight, right? And therefore the numbers can be inflated because of the weight, okay? I want to control these things. So therefore I'm going to say, well, let's pick 4 people, weight the same, age is the same, and let's just give them 4 different drugs and see what happens. So now I am eliminating the variability in the data, which could be attributed to the fact that people weigh differently and people have different ages, right? I control that part of the variability. So therefore, experimental data like this one, when you have blocks, is always preferred way to run the analysis compared to independent samples, okay? You eliminate sources of the variability, so to speak. You're running more pure experiment. Make sense? Okay, so, well, let's be formal about that again, right? I go back to my flow chart. Obviously, I have to start with this one, right? In this example, I'm comparing 3 or more populations. Well, actually, it's 4, right? The purpose of the study is to compare drugs to each other, right? So I start over here, 3 or more populations. Data type, interval, right? My response that I'm measuring is by how much the cholesterol went down, right? And that's measurable. That's blood test. That gives you a number. So data type, interval. Experimental design. Do I have independent samples or blocks with replications? Well, let me tell you what's with replications. With replication means that I perform the measurement again and again and again and again for the same combination of age and drug. Okay? So in my case, I didn't have any replication because, look at that. This line, number 1, corresponds certain age and weight. And I take one pill or one drug, right, and place a person with this specific age and weight on that specific drug for a period of time, right? If I would take another person which has same age, same weight, and I put them on the same drug, and then another person, and another person, right? Then I'm going to replicate the result several times, right? It's like for every combination of drug, age and weight, I do the measurement multiple times, all right? So I place multiple similar people on the same drug and see what the results are. That would be replicating, okay? But I don't do that, right? I take only one person for this age group, and I place them on drug 1, done. It's only one data point. So there are no replications, okay? Blocks, but no repetitions, no replications. Make sense? Okay, so therefore I'm here, right? My experimental design is blocks, but no replications. And then it says population distributions, my friend, are they normal or are they not normal? Because if they're not normal, then you're dealing with non-parametric test called Friedman. If they are normal, then it's a two-way block design. And two-way, why did we call it two-way again? Two-way, it's called two-way because I have factor 1 and factor 2, right? Okay. So let's check for normality. And let's pray that things are normal. Okay, so I'm going to go to the distribution and select just the drug, right? I'm checking these things, drug 1, 2, 3, for normality. So let's go to the analysis window. All right. Well, visually, I don't know what happens, to be honest. I don't trust my eyes anymore, okay? Statistics is all about that. Don't believe your eyes, right? Run the test. So let's run the test. Let's do simplistic thing, right? Let's do the normal quantile plot. Normal quantile plot. Sample number 1, drug 1, what do you think? Looks decent. Drug number 2, quantile plot. What do you think? It's decent, right? Drug number 3, quantile plot. It has some weird variations going on, right? But nothing too extreme, right? At least it follows the pattern. So I'd say, cross my fingers, that hey, these probably are normal, okay? Not perfect, but nothing is perfect in this world, right? We know that because we're humans, right? We're not perfect. Okay, and drug number 4, decent, right? So even though appearances might be deceiving based on the histogram, my normal quantile plot says that these 4 things probably are good to go, right? Normality is satisfied. So therefore, coming back to my flow chart, experimental design blocks, populations are normally distributed, so therefore I have to use blocked two-way ANOVA. Okay? Now let's discuss what hypothesis am I testing, and then let's actually test them. Here is what I'm testing for my factor A. And factor A is something that goes on in columns, right? I have 4 columns, drug 1, 2, 3, and 4. So I'm trying to see if the cholesterol reduction depends on the drug that you're using, right? And my null hypothesis is going to be that average reduction, if I use drug 1, is the same for drug 2, 3, and 4. They're all the same. Note that I don't put any number, right? I don't compare it against 15 or 12, nothing quite like that, right? So I'm just saying that these drugs are all same in terms of average, right? Reduction, which means that my cholesterol reduction does not really depend on the drug. There is no dependency, okay? Alternative would be that at least 2 drugs give me different results, right? So one drug can be probably more effective, another is less effective, and at least 2 of them, they do differ. So that's as far as my columns are concerned, right? But remember, I have a second factor that goes on in the rows. Each row had a matching age and weight, but different rows, they have different characteristics, right? So row number 2 is a different age and weight. Row number 3, yet another different age and weight, right? So my second factor, I would call it age and weight. Because that's what is different between my row 1, 2, 3, etc., etc. So therefore, my second hypothesis that I will test will be exactly like that. All groups have exactly same mean. And I have 25 groups, right? So group number 1 had the same reduction of cholesterol on average. Group number 2, 3, 4, 5, etc. And if that's true, that means that age and weight don't really affect the results. Okay? So when you're testing the drugs, you don't have to pick people based on their age and weight. It doesn't really matter. Okay? Age and weight is not a factor that affects the outcome of your measurements, right? Alternative says at least the groups have different means, which indicates that it is a factor. Okay? It is important to know what's the age of the patient and how much they weigh, because different ages and different weights, they're affected by the drug differently. Okay? That's what my alternative means. All right. Now let's go back to the to my analysis. Well, first of all, this part, I'm done with this, right? I don't need to see distributions anymore. All I did was checking normality. So that part I'm going to close. So let's go back to the data. And just like for the one-way ANOVA, for two-way ANOVA, I have to stack my samples. Okay? And let's see how exactly JUMP does that. So I'm going to use the same menu. We'll go to Tables and option Stack. It will look very similar, right? So I'm going to stack these columns, drug 1, 2, 3, 4. Okay? All right, and now I have to again specify what's the name of the column where the measurements are going to be located, and what's the name of other columns, right? So here I'm going to say data. Now, really, data is not a good word for that, right? So what am I measuring? Cholesterol reduction, right? Cholesterol reduction. And the other column would be drug, right? Because it's drug 1, drug 2, drug 3. So different drugs. And what happens when I click OK? Let's see. When I click OK, it actually creates 3 columns for me. So JUMP, thank God, is smart enough to recognize. And let's actually keep both data sets together just to see what JUMP did. Okay. Well, number 1, JUMP actually realizes that this thing, which is labeled, by the way, as a age group, right, from 1 to 25, that labeled as an ordinal data. Okay. So categorical data, that probably represents a grouping factor, age and weight in our case, right? But whatever it might be, okay? We just numbered them from 1 through 25. But the important thing is that this is not a numerical measurement, that's actually a label for the group, right? That corresponds to a certain combo of age and weight. And therefore, look at that. First age group 1, 1, 1, 1. So that corresponds to these observations, right? First line. And then it's drug 1, drug 2, 3, and 4. 6.6, 12.6, 2.7, 8.7. So what JUMP did is it said, okay, apparently there are 2 things going on. Obviously, factor number 1, factor A, is something that goes on in columns. And this is factor B, it looks like. So therefore, let's actually create 2 different, and these are 2 different factors of study, right? My age group, 1 through 25, and my drug. So this is my factor A drug, and this is my factor B, age and weight group, okay? And these are just measurements that were stacked together and spread according to these labels, right? Positioned according to these labels. So I'm actually prepared to go ahead and study the effects of this thing using 2 factors now, okay? Now, the analysis now is done a little bit differently, actually. We're going to use yet another new menu that we never used before, okay? And that menu is Analyze, and then Fit Model. Not just Fit Y by X that we use for independent samples, but Fit the model. Also, there is a shortcut right here for Fit Model. So see, all important things that JUMP can do, would it be a distribution or a test, they all pretty much come from here, right? These shortcuts pretty much give you the entire thing the entire set of sets. So analyze fit model, and what's my dependent variable that I'm trying to investigate? Something that I can measure numerically, right? And that would be cholesterol reduction. I'm trying to see if my cholesterol reduction depends on the drug that the patient is taking, and also it depends on the weight and age of the patient, right? So the response variable, the dependent variable that I'm trying to investigate, is whatever this numerical I'm studying. That would be cholesterol reduction. The rest of the variables I have to place right here, okay? Model effects. So the factors of the study, that would be my age group and drug, I'm going to add to this section, okay? So I'm going to study the effect of age and the effect of the drug on the cholesterol reduction. That's pretty much the easiest way how you can view that setup. And then I click the run button, and it creates a whole bunch of different things for me. But the important output is at the very bottom, okay? So analysis of variances and effect test, all right? So really what how many hypotheses do I have? 2, right? Well, 4 if you count null and alternative, right? 2 different things, right? I'm studying the effect of factor A, that would be drug, and I'm studying the effect of factor B, that would be age and weight, okay? So therefore, how many p-values do I need? I have 2 hypotheses for factor A and factor B. I need 2 p-values, right? Look at the bottom. Age group is my factor B and drug is my factor A, right? So here is my p-value for the factor A drug. What does it say? 0.0007. Small p-value, right? What do I do with this? Keep the null or reject the null? Reject the null. So let's go back to my null and alternative. Here's factor B for the age and weight. Here's factor A. My null was saying that all drugs are the same and the reduction of the cholesterol really depends on them, right? Is that the case? Nope, that's not, because I just rejected the null, right? So therefore, it does matter which drug you use. So pharmaceutical company now should investigate out of these 4 drugs, some are better, some are worse. Probably they want to go with the best one, right? Not all these drugs give you the same result. That's our finding number 1. And what's the finding number 2? Age group. It had the very small p-value, less than 1%, much less than 1%. So once again, I reject the null in favor of alternative, right? And let's go back and see what was it. My null was that all groups were the same in terms of reduction of cholesterol, or another way to say it is age and weight do not affect the effectiveness of the drug, right? And in fact they do, because we rejected the null. It tells us that groups, in fact, are different. The drugs affect different people with different ages and different weights differently. So basically it's a recommendation for doctors pretty much, right? That every time when you have a patient, you must consider how much they weigh and what is their age, because the effect of the drug will depend on that. Okay, it's not as straightforward as just give them the script and send home. Okay, one more thing that I wanted to point out. That's pretty much it, right? That's the result of our analysis, right? Again, ANOVA is a smoke detector. It tells you that there is something going on, there is a dependency, but it does not tell you what precisely is better and what is worse and how things are changing as you go from drug to drug or from age to age, right? But we can kind of informally judge that. And for that, we can use, so here is our plot, here is another plot. So for example, for the age group, right? What I can do is ask for least squares mean plot. Least squares means that for each level of my factor, I have 4 levels of drug and I have 25 levels of age, right? For each factor, it will try to fit the best point inside this group. And then if I ask for the plot, this is how it looks, okay? So as my ages progress from 1 to 25, whatever that is, by the way, I don't even know, right? Age group number 1, what is that? No idea. It can be people, under 150 pounds and between the ages of 20 and 25 years, right? It can be that. So, however the groups were created, combined, I have no idea what that means, right? But all I can say is, as I change my test patients, test subjects, right, from groups, starting from group 1 and all the way through group 25, what happens in terms of the drug effectiveness? It goes up, right? Because people lose more and more cholesterol, right? So whatever happens in these groups from 1 through 25, the drugs are actually working better, right? Better and better. So that's what this plot tells me. Now let's take a look at the drug plot. Same thing. I'm going to ask for the least squares mean plot. And here is the plot, right? And what does this plot tell me? Let me make it bigger, if I can. Yeah, let me make it bigger. Basically, it tells me what's the average effect of the drug, right? So, what do you think about drug 1 and drug 2? About the same, right? No difference. Drug 3 probably is worse, right? Because it results in lower reduction, right, of cholesterol. And drug 4 probably is the best out of them all, right? So that's kind of informal way to see which direction your investigation could be taking the next turn, right? Now that I'm looking at these plots, I'm saying, well, if I want really to pick between the drugs, my comparison should heavily involve drug 4, right? Because it appears to be doing best out of them all. So now it makes sense for me to run, for example, drug 4 against drug 1, see if there is a difference, 4 against 2, and 4 against 3, right? That probably is the next step that I want to take here. Okay? Make sense? All right, ladies and gentlemen, that's all I have to tell you about statistics today. Homework is posted. Tomorrow we're going to start talking about simple linear regression and also chi-square test for independence. Okay?